4th of July weekend and start watching welding videos. We talked about the thermodynamic nobility, which is a pure energetics. And if something's thermodynamically noble, it means it can be immune to corrosion. And about the only things that really are immune are these things at the top. But practical nobility, things that form a very stable oxide skin, there are quite a few. I mean, you get down here to aluminum and stuff, zirconium, because some of them have very, very stable oxide skins. But you can see by these lines across here, the order completely reverses when you start talking about passivation, this coating on the surface. Okay? So, oops, what's going on here, guys?
Is that line at 23 the divide between immune and non-immune on the left?
That's probably 0 volts on the standard calcium metal electrode, which is an arbitrary scale. Okay. This is the galvanic series in seawater. I'm sure a number of you have already seen various versions of this. This is a simple one. Graphite is one of the most noble corrosion resistant materials we have. Magnesium is one of the most reactive materials we have. I think I told you the story about the Navy at Port Guanumi made magnesium graphite composites that were super corroders. Okay? Got an anode and a cathode, and you mix them together as powders, put them in seawater, and you start seeing gases being evolved. Okay? You're breaking down the water because you got 0.2 volts and 1.6 volts. 1.8 volts, you only need 1.2 volts to break down water. Okay? And you'll electrolyze the water. So we got other things in here. Now, there are some interesting things. When it says titanium iodide, you say, what's that? I showed you the crystal bar of zirconium that was made from zirconium tetrachloride. Titanium is made by the same process. If you saw a crystal bar of titanium, it would look the same, just way a lot less and a little grayer rather than silvery, like zirconium. But they use titanium tetraiodide. Okay? Those are old processes developed after World War II, and they're more expensive. We have other processes of making zirconium and titanium that are more complex now from their ores. But in any case, this is titanium iodide process. We get down here, and nickel 200 is a fairly pure nickel. This is a pure nickel, 99.9. Stainless steel, 216 is a manganese nickel, replacing a manganese stainless steel replaces manganese, replaces a lot of stainless. It's a cheaper version, doesn't have as good a corrosion resistance. 304 is the garden variety. That's 18.8 stainless. If you look at kitchen utensils and stuff, they say 18.8. 18 chrome 8 nickel. That's close to the original stainless steel in 1910. 430 is a ferritic stainless with no nickel. In any case, what some of these will show, they'll show passivated and activated. The active will be more corrosive. This is more corrosive. This is the anode here. Than the passive. And the difference is, for stainless steel, all you have to do is get rid of any free iron on the surface. Put it in an oxidizing bath. To passivate 304 stainless steel, you come off the rolling mill, and it might be partially passivated, it might be not fully passivated. If you just stick it in some nitric acid for a few minutes. Nitric acid is an oxidizing acid, eats away the free iron on the surface, forms a nice coherent chromium oxide skin. It's actually a more complex skin than that, but we'll just call it chromium oxide skin. If I want to activate the stainless steel, because I cannot plate, if I wanted to plate copper or nickel onto the stainless steel, and it was just passivated, I could electroplate it, but it would just flake off, because you're really just plating onto this passive surface, which is a ceramic surface, if you will. I mean, it's a number of monolayers thin, okay, but it will flake off if there's no adherence. If you really want to plate to stainless steel, you have to activate it. You put it in hydrochloric acid. Those chlorides eat away the oxide, leaving an active surface, which is very corrosion prone. And now you can plate to it, and you'll get metal-metal bonds, okay, as opposed to an oxide surface in between. have had people come in once every couple of years with a piece of steel and they say, this was supposed to be stainless and it's not stainless because it's rusty. And I say, no, it's stainless. No, actually, the first thing I do is take a magnet. And if it's non-magnetic, I say, no, it's stainless. It's just, it's active, okay? And active stainless steel rusts. And some people say it's stainless, not stain-free, okay? And in fact, there are different types of stainless steels, like 316 is 304 with 2% molybdenum in it. And 2% molybdenum gives good saltwater corrosion resistance or chloride corrosion resistance. So I didn't bring it, or I forgot to bring it with me. I have a sample. They were making Fenway Franks over here in Everett. They make tens of thousands, of 100,000 hot dogs a day over there. And they have this big tunnel chamber of half the size of this room in cross section, where they just load it up with hot dogs, and they, after they grind up the meat, actually they don't grind it, they liquefy it, okay? You don't know what's in that meat, okay? It says all beef, yeah, it's all beef, okay, but probably all of the beef, okay? We won't get into that. But they actually call these processors of these sausages, they call them meat liquefiers. And it's ground, okay? I mean, you won't find any hard particles, well, you won't find any particles in there. Anyway, so they had done a repair, they had to replace something. And within 2 weeks, what was supposed to be 316 stainless steel cooker was just full of cracks. And I have a couple of pieces, but I have to be very gingerly with it because it's just completely falling apart, and it's rusty in between and stuff. And they had me come over because they wanted to know why their cooker was falling apart in 2 weeks. And I brought it back and put it in the scanning electron microscope. It had no molybdenum in it. It was 304. Someone used 304 rather than 316. It's one of the most dramatic examples I've ever seen of the difference in corrosion resistance. Those hot dogs got lots of salt in them, guys. Okay? So it was a hot oxidizing saltwater environment. The U.S. Navy was interested 15, 20 years ago. They still want non-magnetic submarines. That's one of the advantages of titanium. So they were going to, you can't get a non-magnetic regular steel like HSLA, or even though that would be a new version, or HY. So they were looking at austenitic stainless steels, which are non-magnetic. But they were looking at 6% molybdenum. Now, molybdenum costs about, 1% molybdenum will add about $1 a pound to the price of the stainless steel. Okay, so we've got HY 100, which you make a current submarine out of, at $2,000 a pound, or $2,000 a ton, $1 a pound, roughly. Maybe it's $1.50 now. But it's got alloying in it. I mean, carbon steel plate, you can probably buy it in the world market right now for $500 a ton. You buy alloy steel plate, you might be paying $1 or $1.50 a pound, $2,000, $3,000 a ton. Stainless steel, you're going to be paying $5,000 to $15,000 a ton. This fancy stainless steel, AL for Allegheny Ludlam is a steel company, okay? 6X10, okay? Has some nitrogen to stabilize things. We won't get into all the metallurgy. Actually, we probably covered some of this in the welding metallurgy thing. Allegheny Ludlam, 6 is a 6% molybdenum. 6% molybdenum, you've added about $6 a ton. We're now up to about $12,000 a ton for this stuff. Okay? Still cheaper than titanium, which could be costing you $50,000 a ton. Now you get twice as much titanium because it's lighter, right?
This is kind of a homey question, but is that what they make the drains for out of, like in your kitchen sink and in the bathtub? Because you pour chlorides down that all the time.
Yeah, but it doesn't sit there. Submarine sort of sits in the water.
Sure.
Okay, for a long period of time. No, you can boil salt water in a 304 stainless steel pan, but it's not sitting there for long periods of time. Okay,
so long as you rinse it in fresh water pretty
yeah.
quickly.
It's like I said, you have to rinse the engines to get the sulfides out for the turbine blades and stuff. rinsing things is fine. I mean, I can take a 304 stainless steel thing and put it in Clorox for a few minutes, but not a few hours, okay? Put it in for a few hours, it'll be pitted. Put it in a few months, there won't be anything left, okay? Just eats it away. So it's a rate. And I'm not really going through, the corrosion guys have something called the TOEFL equation, and these diagrams to help you understand what's going on in the anode and the cathode for these reactions in terms of the TOEFL. The corrosion rate is proportional to the corrosion current, how many electrons are flowing. Because it's a chemical reaction with electrons, okay? So if you can do anything to stop the current, I mean, then you can stop the corrosion. And I'll give you an example in a little bit. I told you, you can stop the corrosion by getting rid of the free oxygen, okay? Because it's going to be a reaction of the metal to form an oxide. Well, there's also an electron involved, if you write down the equation. So if you write down what they call the half reaction for the ion, iron metal, 0, plus an electron, 2 electrons actually, goes to Fe2 plus, okay? Or no, I got it. Iron goes to 2 electrons plus Fe2 plus. Okay, that balances this equation. Anyway, so if you write down the whole reaction, there's also oxygen involved in here. Get rid of the oxygen, you can stop the reaction. Get rid of the electrons, you can stop the reaction. Okay, and we'll talk about that when we get to cathodic protection.
Okay, I was going to ask if you get into cathodic protection and sacrificial anodes and how those work.
Yeah, that's a couple of slides coming up. Anyway, so there is this galvanic series, and things can change. You see pure aluminum and aluminum alloys on here are in different locations, different potentials. You get a half a volt here between aluminum and aluminum alloy. Not enough to drive corrosion by itself. You just have something else and get yourself up to about 0.7 volts or 0.8 volts, and you'll get your corrosion. So we got the port bay diagrams and voltage versus pH, pH of the water, the potential, and you have cathodes down here and anodes up here. And you will have immunity down here where the metal just is stable at these voltages and for wide ranges of pHs. You'll have corrosion in very acid or very alkaline, and you'll have passivation often in the middle. And I showed you some of the plots the other day. We'll probably see some in a little bit. So this is just a fancier version of that. This is a noble metal. This is an active metal. What is that? Zinc? Okay, so there's gold. Gold just is noble in water, okay? It doesn't corrode. Zinc, so we could build gold submarines. They're heavy, okay? It'd sink really well. Zinc is only stable, zinc hydroxide, in a very narrow range. Very alkaline, and all of a sudden the zinc hydroxide starts to become soluble and you lose your passive layer. Aluminum oxide in a wider range, this is practical nobility. Okay. Here are your anodes on the ship. Okay. So these are nice new anodes, nice new person, painted ship, nice anodes. This is one that's been there for a while. Okay. And the anodes typically are mounted to a piece of steel because you don't want to mount directly to the anode. It tends to corrode away, whatever you fasten it to. And they use aluminum. They also use magnesium. One of the largest uses of pure magnesium in the world, probably the largest use, I think it's like 40% of all the pure magnesium is for anodes in water heaters. Okay. Now, we don't have to have them in the plastic lined heaters that people are starting to use now, but all the steel, whether it's stainless steel or copper or anything, they always have a magnesium anode. And it says right there in the manual to change your anode every year. How many of you have ever changed your anode? I've talked to plumbers. They don't even know what an anode is in the water heater, okay? So they don't know about changing them. And in fact, people don't change them. And sometimes if they don't, well, it will corrode away, but they basically extrude the magnesium on a steel wire. And then they connect the steel wire, and just hang it in there, and it just slowly corrodes away. forms magnesium hydroxide. No health problem because you buy magnesium hydroxide and we call it milk of magnesia. Okay? You drink it when you're constipated. Okay?
So if you ever don't have any in the house, just pop that off the top of your water heater and lick it.
Well, it's not quite as concentrated. But yeah, you could. Okay, it's not, it's not toxic. Okay, which is one of the reasons they can use it. Someone asked me or talked a little bit about duplex systems where you have galvanized steel and then you paint it. This is a whole book on this topic. This comes out of that book. Has some nice colored pictures. This guy in the Netherlands has spent his life looking at corrosion of galvanized steel, and it forms all kinds of complex carbonates and hydroxides and stuff. The interesting thing that I learned is, oops, if you actually take galvanized steel and you freshly galvanize it, freshly galvanized, and you paint it. Actually, you can't paint it fast enough. You hot dip galvanizing, you just dip the steel in a big zinc bath, leave it there for a couple of minutes, pull it out, and the zinc has started to alloy with the steel, and now you have some zinc on the surface, 1 or 2 thousandths of an inch thick. And it might last for 30 years in the atmosphere. Okay, it might last one year in seawater. We talked about that. But if you try to paint it right away, the paint will flake off, and that's because it actually in the air forms zinc hydroxide, and the paints will not adhere to the zinc hydroxide. If you let it sit there for a year, the CO2 in the air will change it to a zinc carbonate, and you try to paint it, the paint sticks. So if you go over here to Duncan Galvanizing in Everett, where they have this big tank about, I guess it's about 3 times long as this room, and they can put whole steel I-beams in there, and they're galvanizing things for construction. They have a bunch of guys with small little abrasive wheels. When they put it in there, these guys will be abrading away that zinc hydroxide layer that formed coming out of the bath, the zinc oxide layer, I guess, that comes out of the bath. And then they can paint it, but they have to go abrade the whole surface of some of these things like it's only 1 or 2 thousandths thick. So to see this kind of hand labor doing all this is sort of incredible to see how complex it is. On the other hand, if you let it wait for a whole year, it'll form its own zinc carbonate layer and it's fine. So far as cathodic protection, this comes out of a thing on protecting pipelines. And we got steel pipelines. We got over 1 million miles of steel pipelines in the country. It's actually a very valuable asset for the nation in distributing things. And they bury graphite anodes. Why graphite? Because it's corrosion resistant. But it makes a good anode. It doesn't corrode in the soil. But it can act as the anode, and you make the pipe the cathode. You have to complete the electrical circuit. The soil has to be moist. This would not be a very good circuit in Arizona because the soil is not moist. And I think I mentioned the problem in Belmont, one of the Belmont schools. They put asphalt over the top. The soil wasn't wet, and you basically took away your electrons, okay? But you took away your protective electrons in this case. So aboard ship, you sometimes use anodes, but on subs and a lot of surface ships now, you're using impressed currents. You're not using a battery, consumable electrodes. Sometimes they bury graphite electrodes, sometimes they bury aluminum electrodes. And you basically are just forming a battery and making sure the thing is there. But the protection is there. They go around to the pipelines once a year, put probes in the ground, measure the voltage. They keep track of these voltages each year, and they see if they're everywhere, because they're only putting these anode beds every couple of miles. And if they find that you're getting down to below 0.83 volts, or below 0.83 volts, which is the protective layer, they have to bury a new anode bed. And the anode battery can last for 40 or 50 years. But there's a lot of maintenance that goes along with protecting this billion-dollar asset of the pipeline. Okay?
How does
and
this actually work?
Huh?
How does this actually work? Like what's happening when you electrify your anodes and your cathodes? And...
If we go back to the Courbet diagram, we're making the steel, in this case, down here, by the cathode. This is the cathode at the bottom of the diagram. This is the anode up here. In cathodic protection, we're either going to consume the zinc and leave the steel protected. We're making the steel immune by an electric potential. Okay? It can't react until all of the anode is consumed. Does that make sense?
I think so.
I'm eating up the anode, which is, this is my anode. If this was aluminum, the aluminum would be slowly dissolving away. Turns out the graphite, if you bury graphite, which is more expensive than just burying aluminum, the graphite will not corrode, but it will accept the electrons. Okay? But
So now the
you're
electrons,
getting a current flow. You're pressing a current. There is a current flow here.
and that keeps your iron in your pipe from dissociating into iron 2 plus and
Right, because it's the wrong voltage. If I apply the voltage is, depending on the voltage, plus or minus voltage, I can drive this one way or the other. If it's a positive voltage, I'll corrode. If it's negative voltage, I'll reduce. Okay? This is on the Courbet diagram, it's reduction, cathodic at the bottom, it's anodic at the top. And the Courbet diagram is showing me both cathode at the bottom and anode at the top.
Okay.
I'm now applying current so that the thing I want to protect is always the cathode. And if it's always the cathode, I've seen steel pipes come out of the ground after 50 years absolutely pristine. Okay, like they were put in the day before. Okay?
So if you had aluminum as your anode chilling next to the pipe, would that aluminum leach into the soil and plate onto your cathode?
Well, only if your soil is water.
Okay.
The aluminum's not going to go through the soil. I mean, the transport of moisture, aluminum ions through the, a mile through the soil is going to.
Oh, maybe on a ship where you have your
But on a
anode.
ship, yeah, you could be plating something out.
Yeah.
Okay. Although usually, we're going to get to what's called, actually the next slide, is throwing power. Okay. In all of this, you have what's called throwing power. You got your cathode and you got your anode. Now this is just from some electric field thing. But you guys, you know what Laplace's equation is now? Have you learned that?
A little bit.
Del squared phi is equal to 0? Okay. Phi equals 0. That's Laplace's equation. You guys learned to solve that. Probably. Okay. But that is the equation. If you put the field in here, or you'll get a voltage. Okay, it's the gradient of the field is the voltage, or the gradient of the voltage is the field. Okay, well, I like the here. The gradient of the voltage is the field, and so if you want to plot the field lines, this could be an electrical thing, which is what I'm trying to show it. You can talk about some Van de Graaff generator, so you have an electrostatic field. This would be like the ball on the tip of the Van de Graaff generator over at the Museum of Science. That's a good thing to do, although particularly if it's a rain day.
Yeah.
It's also great for kids. The Van de Graaff generator at the Museum of Science was Van de Graaff's generator here. He was a professor of physics here. And it was still over here at MIT when I was, probably when I was a young professor, certainly when I was a student. Anyway, so these are the field lines. These are the isopotential lines. It's also the temperature distribution. If you're doing del squared T for the heat flow. When I told you that Einstein looked at the diffusion equation, this is the diffusion equation. Okay, where they're talking about diffusion of electrons from one source to one sink. I guess, yeah, I think that's right. Or the opposite. It could be temperature, it could be momentum. Only momentum becomes the Navier-Stokes equation. It's got a few other terms in it because of shear forces and stuff. But the diffusion of shear is Navier-Stokes. The diffusion of temperature is Fourier's law. The diffusion of mass is Fick's law. And the diffusion of electrons is actually Ohm's law, but we never get into the second transient form of Ohm's law. Electrons go so fast, we usually consider it to be steady state. Okay? There's no time dependence. There is a time dependency on electron flow, but it's a very short time. And usually we can just treat our electroisostatic fields as the first law, Fourier's first law, or Fick's first law, Ohm's first law. We don't usually talk about Ohm's second law, because if you do, you actually get getting into quantum mechanics. So you don't have to worry about that. Anyway, across the interface, you get this double layer where you have a voltage potential. This is the very, very narrow layer right up against the surface. It could be 5 atom layers thick. And you have tremendous changes in the electric field, the charged particle direction, the polarity. People like Professor Sadoway, or an electrochemist who's studying corrosion, he starts worrying about these types of details right at the interface, because that's where the chemical reactions are occurring. You got mass going this way, the oxygen going that way, the electrons going that way. Everything's changing position and getting a chemical reaction. Now, the throwing power, okay, depends on the resistivity of the medium. If you got 18 megohm reactor water, or 14 megohm reactor water, it's so much resistant, there's no current flowing electrons to do the protection. So you can't use cathodic protection in reactor water. It's too resistive, no electrons. In seawater, where you have very good electrical conductivity, you can actually get throwing power from a zinc anode for about 10 to 30 feet. And if we went back to that chip, okay, these things should all be within 10 feet of each other. And they're actually considerably closer than that. They can protect over 30 feet, but you have scales that form on them and things. In freshwater, we're talking about inches, like a foot. So if you're a Coast Guard guy and you're in the Great Lakes, yeah, you may have anodes, but you got to have them a lot closer together. Okay? And that's why, to a certain extent, impressed current, where you don't have to have a source, a point source of zinc, okay? Or you galvanize the whole thing, so it's coating the whole thing, okay? But there is this throwing power problem, and there's a big difference. So you Coast Guard guys need to understand that fresh water is different than seawater. The Navy guys did. Never heard of fresh water. You never drink it on board, right? Okay. We've talked about this a couple of times. I mentioned there is this Corrosion chemical in the presence of a gaseous phase. That's the current version of it, and it's in nice colored things if you want to pass that around. And people can see that's basically equilibrium diagrams for sulfidation and oxidation and things. But it's just people make a career out of doing these plots, and here's one of the plots for iron oxide. Okay, this is out of that book. And now we're plotting, what are we plotting? Plotting temperature across here, and we're plotting electrochemical potential up here. So it is a Corrosion diagram, and it's an electrochemical potential in terms of hot corrosion. And you can form iron chlorides down here, form iron oxides, iron hydroxides. You might have stable iron over here. And if you want to understand why your turbine blades are corroding, and you can see if you start getting chlorides in there, they're going to form big areas where you're going to form iron. You'll find iron chloride at the cathode, and you'll form iron oxide at the anode, and that's not going to be. You're going to form galvanic cells, okay, little regions that will fit through, which is what you saw with turbine blades. Okay, rate of general attack of steel. I mentioned some of this, I guess, yesterday or the day before. The general rate of corrosion of steel is about 4,000ths of an inch a year. Ranges between 2/10 and 10,000ths of an inch, 2,000ths of an inch, 2 mils and 10 mils a year. And the U.S. Army Construction Engineering Lab in Urbana-Champaign, anybody here, University of Illinois grad? Okay. and I won't tell you about the moral plot. But anyway, they own 25,000 underground storage tanks. And now, it used to be the military wasn't responsible for any environmental things. You guys don't know that, but 30 years ago, the military basically, and Congress basically exempted the military from all kinds of environmental problems. And you used to use tributyl tin in your paint. Anybody ever heard of TBT? Okay, you heard of it, right?
I've heard it's a problem. I mean, a couple Superfund sites because of it, right?
Yeah, well, the only people that I know who ever used it was the U.S. Navy. And if you want to get rid of all the barnacles, just paint that ship with paint that contains tributyl tin. Gets rid of the barnacles. It also gets rid of every other mollusk in the harbor, in the part per billion range. Okay, of tributyl tin. And so you take that Navy ship, float it into this harbor, and you'll never have any oysters or scallops or any, they all die. Okay, it's tremendously toxic. And so, in part because of that and a few other environmental problems you have, Congress decided that they were no longer going to exempt the military. We used to have sort of an exemption for these things for military necessity. So now you actually have people who are going to make sure you are environmentally pure, just like, it's just, right? Huh?
Yeah.
It's people getting paid salaries to screw up your life.
We actually can't put, in the shipyard, we can't take fresh water and put it into the salt water.
Yeah, I mean, and it's not just the Navy that does this. I mean, I know a guy who's looking at he was from professor from Wyoming and went to Alaska, and they were developing a gold mine. It turns out the river water had 7% arsenic in it. 7 ppm, not 7%. 7 ppm arsenic. This was the natural river water in this river in Alaska. They built the gold mine, and the EPA said they could not put more than 1 ppm or have more than 1 ppm arsenic in the water they put back in the river. So they had to clean up the river water to better than it was, and then throw it back in the water to repollute it, right? There's good use of energy, right? So it's just like you have to clean up the fresh water before you put it in the seawater. Right? Or you can't. You said you can't put
fresh water into the seawater.
Yeah, well, as much fresh water as you guys have, and put it in there, you're going to dilute that ocean, right?
Yeah.
I mean,
We put tarps over the ocean when it rains.
don't try to reason with an environmentalist, okay?
I don't.
One time, Congress decided they were going to outlaw anything that could cause cancer. Okay? And so, someone finally convinced them not to pass this law when someone pointed out that oxygen can cause cancer. Or no, it was not causing cancer. Anything that could degrade DNA was going to be the standard. And this is about a bunch of liberal arts people, trying to play scientists. And they said, well, DNA is fundamental to life. We're going to outlaw anything that degrades DNA. And it turns out one of the best promoters of degrading DNA, and it does it by combustion. Okay, oxygen is excellent thing to promote combustion, right? Is oxygen. So Congress was on the verge of outlawing oxygen.
Kind of surprised they haven't yet.
Well, the Norwegians were on the verge of outlawing. They had a campaign to outlaw chlorine from the environment. Okay. Anyone tell them how much chlorine was in the ocean?
That'd be impressive.
And anyway, they tell me Norway is near the ocean. Anyway, rate of general attack of steel. So the Army did this big study of 25,000 underground storage tanks to know what their liability going forward was. The soil resistivity in ohms, you got to have, that is going to affect your corrosion rate. You now understand why, because you've got to complete this corrosion circuit, whether it's anode or cathode. If it's going towards the anode, it's promoting corrosion. If it's coming from the other direction, it's stopping corrosion. So the direction of the current is important, but just the general resistivity tells me how much current I might have. The soil pH, you know that from the Courbet diagram. The soil moisture. You gotta have some vehicle, conductive vehicle, which is related to the soil resistivity, with the moisture, whether it's saturated, damp, or dry. And they have these little rating points because they came up with the regression formula. And then turns out the ratio of the resistivity and the soil pH difference in the pH value from one spot to another is important. And the sulfide content, oxygen and sulfur both promote things. Mostly the sulfide content is important because there are certain types of bugs that are sulfurous producing bugs, or they eat sulfur compounds and they produce sulfuric acid. And acid promotes corrosion, you know, from the four-bay diagram now, right? On that side of the four-bay diagram. So, big 4-point weighting factor there for the presence of sulfur, which means you probably are going to have some sulfur eating bacteria. So here's their plot, soil aggressiveness value versus time to forming a leak in the tank, and this is real experimental data. And here's my range in typical 4,000ths. If you got something that's 1/10 of an inch or 1/8 of an inch thick, guess what? In 25 years, you'll eat through 1/10 of an inch of steel. There it is. You can say, well, maybe it's around here. Well, 80,000, there's some pitting that goes on. But here's the scatter plot. Some things last forever. That's Arizona. Some things go in 6 years to a leak. And that's probably sulfur-producing bacteria forming acid pitting and everything else. I mentioned this next one. This is how the general scale can protect a ship. I tried to draw this for you a couple of days ago, last week or something. Exposure time in days, so here we got a year, here we got 2 years. This is the attached thrust in the lower parts of the ship. Here's the flexing detachment of partially protected rust. And the corrosion rate is basically constant if you keep on flaking off the rust. But if you actually measure it, it's going up and down because the rust forms, protects it, and then goes away. So there are some things that we have to worry about. In particular, you guys got to worry about corrosion in boilers. This was something I worked on in a zinc smelter in British Columbia, and they basically had a lot of sulfur, but they also had some thallium in their ores. And they basically started out with carbon steel. And they put the carbon steel in this boiler. This was a big boiler. It was like a big utility boiler. It was about 6 stories tall. And these were the walls of the heat exchanger, one of the heat exchangers for the boiler. And they had water going through here that they were heating up and using in other parts of the process for steam and stuff. After about 1 or 2 years in production, they went from a thickness like this in the steam tubes to a thickness like this, and then they decided, that's probably corroding too fast for us. And this is because they had these sulfur compounds and other stuff. It was hot steam. And so they decided to go in and plate the whole thing with Inconel, okay? And they did this by a welding process. Guys would go in there and they had to have suits on because there was thallium on. Thallium is it's on the kind of the same area as lead on the periodic table, only thallium will diffuse through your skin and give you heavy metal poisoning just on skin contact. So these guys had to go in their spacesuits and do their welding inside this boiler, okay? You know, breathing air from outside, they looked like they were wearing spacesuits. And in fact, everything was fine except they had one little pinhole where they didn't get the Inconel in and it ended up blowing up and cost $40 million of the damage when well, actually in this case, they had a layer of coal on at the bottom of this boiler, and when the water came out and formed the steam, you got what's called a water gas reaction. In the old days, before we had methane from drilling oil wells, they used to have flame lights for street lights in the cities, and they would use the water gas reaction. I remember it's one of the things I had to calculate 15 times as an undergraduate where you basically take steam and react it with coal, and you'll start out with carbon, coal, hot coal, plus steam, and you'll get a mixture of CO plus CO2 plus, you still have some water carrying over, plus hydrogen, okay? Essentially, some of the water steam will react with the carbon, and you'll form this, which actually is a flammable mixture of gases. And we got to calculate that under lots of different conditions of how much CO, CO2, H2, H2O. And then they told me about Ellingham diagrams after that, and I could have just done it graphically in about 1 minute, okay? But I used to get it too the hard way. This was considered teaching.
It's good for you.
Yeah, it's good.
Builds character.
Yeah, that's why I have it on now. I don't do it anymore. In any case, where was I going with that? Anyway, so they had a steam, I think they had a steam reaction, and they built up flammable gases and shooting hot other gases in there, and just had a lower hydrogen or water gas reaction in the boiler. In any case, here's a book, which is actually 2 books. And I used to recommend in the first edition, these are both second edition, the first edition costs like $30, and I actually used to recommend to the 2N students that you guys go out and for $30 a piece you could afford to buy these, okay? They're now like 150. Unfortunately, you know, a lot of companies have found that there's value to some of the things they write. But Nalco is the world's largest water treatment company for boilers. You know, most utility plants, they hire Nalco, and Nalco comes in and checks their water chemistry. The Navy hires you, okay? And you have to maintain the water chemistry of your boilers. But if you have a boiler failure and you don't know what caused it, the first thing I do is I go to the Nalco book, because these guys have seen it all. And they wrote a book years ago. It's now in second edition. And if you have a cooling system, they have a book on cooling water systems, okay? Unfortunately, actually, if you went to Amazon, you could probably find the first edition cheap as a used book. But by the same thing, you can find a lot of this stuff off the internet now. But there are certain books like this that it's worth at least knowing that they exist, okay? Because there's going to be some explosion or something, and people are going to come to you and say, why did this occur? And you go and you look through your little book, and you come back the next day and say, well, this was sulfidation due to blah, blah, blah. And it's all explained in there. It's neat to be able to act like an expert. So this is a book called Marine Corrosion, which is no longer in print. But if you're interested in the corrosion of steel in seawater, and Francis LeCue, who the International Nickel Corrosion Research Laboratory is now named after him. He was back in the 1940s or so. But he wrote a book called Marine Corrosion, and this is the oxygen versus depth. The oxygen corrosion rate, oxygen in milliliters. I'm sorry, this is a depth, okay, in thousands of feet, so we're coming down to 6,000 feet. Somewhere in here is the limit of what the Navy usually worries about. That's classified, and I will not tell you what it is, because you probably know it better than I do. But anyway, this is within the range of how deep submarines go. Oxygen content or corrosion rate. So here we have oxygen. Lots of oxygen in the surface because we have waves stirring up the air, mixing in some oxygen. We have ASI carbon steel, 1010 steel, and we also have low alloy steels, which would be things like HY steels. And gee whiz, the corrosion rate is directly proportional to the oxygen concentration, okay, as a function of depth. And one of the advantages we have in a lot of the deep sea stuff, where these guys are doing oil drilling at 6,000 feet, is they got low oxygen, okay? And I've been telling them a lot of their corrosion problems are that year the thing was sitting up on the dock before they buried it in the ocean. A lot of their hydrogen embrittlement probably started when it was sitting there waiting to go into the ocean, not once it gets down there, okay? But it doesn't fail until it gets down there, right? This is splash line attack because there's even extra oxygen right at the surface. And so here's basically the type of attack. Free oxygen is required for corrosion, and again, if this fish can't breathe. And so you get this preferential attack right at the splash line. Typically what people do nowadays is they, for pilings and things, they'll come in and they'll spray a coating on there. You know, it could be a corrosion preventive paint or whatever, right at the splash line, because your rate of corrosion attack can be 5-10 times as great when you have all that extra oxygen. If you go to LeCue's book, he'll show the rate of attack of stainless steel, typical corrosion rate in thousandths of an inch per year. Good stainless steels have a very low corrosion rate, or actually these are nickel, chrome, aluminum alloys, these are your inconels, and titanium have no corrosion. The 316 and 304 that we talked about, generally are pretty good in seawater and stuff, but pitting is the problem. And you can have very severe pitting, such as in the Clorox that my mother-in-law used. Yeah, there's not a question, that's stretching, okay. And here's your Monels, okay? 2/10 of a, actually Monel might be down further. Okay, anyway, it's down here, okay? Copper, Admiralty brass, aluminum bronze. Here's your nickel, aluminum manganese bronze. This is your propellers. 1 or 2 thousandths of an inch per year, okay? So, but the real problem here, these things can be 1/10 of an inch per year, okay? Goes way out there for the pitting that goes on. I talked about velocity corrosion or erosion, that if you form a nice, strong protective oxide, you can have very high velocities, like 12 feet per second. That's a pretty high velocity of a pipe. But copper can go at 3 feet per second. Typically in your home, you might be in here at the 3 to 6 feet per second for plumbing in a home. But the copper can fall apart due to what he keeps calling impingement attack. But it's basically the small particles of solids just eroding away that soft copper oxide. You get a harder oxide on the copper, like aluminum oxide on aluminum brass, or the Monel, the cupro nickels. So here are the principles again to wrap up. Most metals, one that exists is either oxides or sulfides, except gold. Metals may possess inherent nobility or practical nobility. 90% of metals are practical nobility, and the other 10%, it's only usually when you've got cathodic protection giving them inherent nobility. And that's the difference, if that helps you understand what cathodic protection is doing for you. Moving it down to the lower part of the Courbet diagram by an electrochemical current. But you gotta have current. You can't just wish you had current. Right. Free oxygen is required. Moisture provides the throwing power or the path for the electrons to flow. You want the electrons to flow if you got cathodic protection. You don't want the electrons to flow. If you don't, then you're just getting corrosion. Because one will be anode, one will be cathode. Localized corrosion, and there's all different types of this, is due to local electrical differences caused by breaks in the coating or dissimilar metals, or oxygen concentration itself, or virtually anything else. I mean, this is where President Truman once said he needed a one-armed economist. You ever heard that story? Because economists always say on one hand and then on the other hand, okay? And I've changed that to most managers would like a one-armed metallurgist, you know, or a one-armed corrosion engineer. Because on the one hand, and then on the other hand. Do you want current or do you not want current? Depends on whether it's cathodic or not, okay? And that, in fact, is important in a lot of things. There's something called, and if you go look into the Metals Handbook, which is this 25-volume set of metallurgical encyclopedia, you'll find people talking about stress corrosion cracking and hydrogen embrittlement, okay? And in 70% of the time in that big encyclopedia, it's written by thousands of metallurgists, I wrote a section in there, they will treat these as exactly the same. They're not exactly the same, but they're almost the same. And the simple answer is this occurs at the cathode, and this is the same process at the anode. And I never understood this until there was a heat treating shop over here by the airport in Boston. And they were making the steel toes for steel-toed boots. Okay, and they have to heat treat those. Those are hardened steel toes. And they were using a salt bath heat treatment where you basically take, in this case, sodium nitrite and sodium nitrate. And one of them's NO2, one's NO3. But they had a mixture, and you were supposed to. This was a big swimming pool. Okay, it was probably 2.5 times as long as this room and 1/3 of the width, and it had about 4 feet of salt bath in the bottom. And they were replacing their salt bath. And ordinarily, this thing gets heated up to 800 degrees Fahrenheit to do the heat treatment on the steel toes. They make a lot of steel toes boots. And now, of course, we use plastic for a lot of the steel toe boots, but they're not steel toe anymore. In any case, their steel tank cracked and caused millions of dollars worth of damage. And I had to go over there, and it wasn't, the tank was a welded carbon steel tank. And I thought, I read the scientific literature, and it said sodium nitrite, sodium nitrate. It was stress corrosion cracking. And so the guys I was working with wanted me to do a test. We did a laboratory test. We made the steel the anode. Because in stress corrosion cracking, you're getting corrosion at the anode. Okay? We could not crack those. I mean, all you have to do is you just take a piece of carbon steel and you bend it into a U shape. This is a pretty sophisticated test. Put a bolt through the bottom so it stays in the U shape. Now I have a tensile stress on the outside of the bend, right? You put it in a bath. In this case, it was a sodium nitrate solution, and we applied a battery to it. We could not get it to crack. And I was starting to get sort of embarrassed after a month of this testing. It wasn't continuous. You kind of leave it in for 3 days and see if he got it. We could not get it to crack. And finally I thought, well, maybe that paper I read got it backwards. And it wasn't stress corrosion cracking. All we had was hydrogen embrittlement. So I said, change the alligator clips on our little setup. Bang! Within 5 minutes we cracked it from hydrogen embrittlement. So there is a difference. It's the actual same physical process, but one occurs at the anode and one occurs at the cathode. You now know more about the difference between stress corrosion cracking and hydrogen embrittlement than 90% of all metallurgists. Okay? It took me about 20 years to find out the difference. And you find things in the literature that don't explain it properly. So we talked about velocity problems, erosion, cavitation, fretting, some sort of mechanical action, whether it's bubbles falling apart in cavitation, mechanical rubbing and fretting, erosion due to particles in the water eating away the surface oxide. But again, you're getting rid of that passive layer. Dealloying, I didn't talk too much about, but basically brass, you put it in certain types of acidic waters and the zinc will leach out and leave porous copper behind. Stress corrosion cracking, I just talked a little bit. Turns out, well, maybe I will tell a story here. Stress corrosion cracking. I'll hold that. Corrosion fatigue, we've talked a little bit about. And hydrogen attack you will get in spades in the welding metallurgy because hydrogen embrittlement is still a problem. So I won't talk about that as far as that goes. So I'll finish up with a story because I always prefer to tell stories and lecture. And this is one where the Navy's the corrosion leader, right? But this came from, what color is this? What service did this come from? It's gray. Navy gray. These were These were Navy washers on a Black Hawk or a Seahawk helicopter. Or if you're a Coast Guard guy, you call it a Jayhawk, right? If you're Army, you call it Black Hawk. In the Air Force, you call it, what do they call it in the Air Force? Some hawk again. Can't remember.
Black Hawks is whatever it's called.
Are they Black Hawks in the Air Force? Well, maybe the Air Force doesn't have enough of them to worry
Maybe we
about.
don't.
Okay, but anyway, it's the same, Sikorsky builds the same aircraft for all the services, and it's the Hawk. It's also the presidential helicopter. It used to be, I think it still is, not the presidential helicopter.
No, Marine one's not.
Okay, but it was when this happened. So we had a night vision goggle Army training exercise in Arkansas. This is an Army steel washer that held these aluminum washers together. And you can tell it's Army because it's Army green, right? But what happened is that, and actually we can pass the two of them around, they don't like to use keyways to hold the tail rotor to its shaft because keyways are stress concentrators, right? So they just use tapered shafts and they squeeze the shaft onto the cone, okay, for the tail rotor, and they tighten it down to the proper torque. And if you put those holes together, you'll see there's there's one fewer hole on the nut than there is on the washer, okay? And so you can torque it, and there'll always be one hole that lines up, and you put a set screw in there, and that holds it to the proper torque. A pretty sophisticated way to hold something on, but you like to keep your tail rotor intact for various reasons. So they're on this training exercise. They lost their tail rotor control. What happened is they had stress corrosion cracking on the washer. It was an Army washer. All it had was these Navy washers. And killed 6, there were 13 guys on the aircraft, killed 6 of them, and one of them was in a coma. Anyway, it was a nasty accident. And so they started looking into it, and they found this is the same type of thing. This is 6061 aluminum with a T6 heat treatment. Now I told you the difference between T6 and T73 before. And T6 has a stress corrosion cracking fracture toughness K1 of 6061 T6 might be 40 KSI square root of inch, but K1 SCC was only, as I remember, 8. You lost 5 times your fracture toughness because of the corrosion. If you had gone to a T73 heat treatment, everything would have been fine because you would have had a much higher, like 30 to 35 for the K1 SCC for the overage. And that's what we do in the heat treatment of the aluminum alloys now. We don't use, when we're worried about stress corrosion, we don't use the T6 heat treatments anymore. But anyway, so the interesting part of this story was, aside from the fact it was also the presidential helicopter, the Sikorsky builds a number of different helicopters, and they keep the engineering teams separate from each other for each type of helicopter. And they had discovered this stress corrosion cracking problem on another helicopter, okay? And they had fixed it. They had gone from the T6 heat treatment on this washer to a T73. And when they discovered this, they said, oh, we should tell some of the other aircraft groups that there's this problem. So at the time, they had ordered, there were 1,300 Hawks, Seahawks and Black Hawks and stuff around in the world, and so they ordered 1,300 of these washers. This washer cost at the time $400 because it's precisely machined, and it also has this what they call Martin hard coat, which is an aluminum oxide surface and a wear surface in here, reduce the wear and stuff. It's pretty sophisticated. It's a lot more sophisticated than just looking like a washer. But it's a $400 washer. They had 1,300 of them on order. It was going to take 15 months to get them produced. The helicopter went down after 11 months. So they actually knew what the problem was. They just hadn't had time to replace them. You would have thought that maybe they would have done an inspection, particularly since when they went out to look for things, the reason I was able to get some of these in the old T6 heat treatment was because the Navy had them. They were called spares in the supply system. And they found some of them were cracked in their plastic bag, never been used.
Is that what the crack is?
Well, the reason these two have a saw cut in them is I took an intact washer, 2 of them, and we measured the residual stresses by just sectioning it, okay? There are residual stresses in this that it turns out, I may have the numbers wrong, I'll just say the residual stresses were 10 KSI. Actually, as I think about it, we measured 8 KSI and the K1SCC was 5. But in any case, the point is, the residual stresses from the heat treating and producing this, where you heat it up, quench it down, and then reheat it to agent, would produce residual stresses, and those residual stresses were sufficient to crack it on the shelf, okay, without even being in service. And the Navy, being the corrosion leader, they went on the aircraft carriers or whatever, and they had some of these spares, and they were already cracked sitting on the shelf, okay? So they knew about it, they hadn't fixed it, and the helicopter went down. I thought it was very interesting that, I wonder if they would have fixed the president's helicopter first. I bet those guys might have been doing a little more, those Marines might have been doing a little more maintenance. Since people knew what the problem was, and they really should have been doing the maintenance to check, but obviously the guys that lost their lives didn't have the advantage of knowing what was going on.
Is there a creep to that?
It's not creep, it's just stress corrosion. It's just a sustained stress. And I told you that the difference between these stress corrosion cracking, oh, it's right here. One's hydrogen embrittlement, one's stress corrosion cracking. It's the same process. You're jetting hydrogen in a cathode and you're doing corrosion at the anode. This is the stress corrosion cracking at the anode in this case. But it can be a delayed response for various reasons.
So you'd start to see it create before critical failure.
You would find a crack ahead of time.
Right.
But you may only have 5 hours, 10 hours from when you would find a crack to when it was gone. Okay? Once it starts growing, it can go pretty quick. Okay? In hours. And they should have been checking. Okay? But it's just, and the
They should
thing
have been
is,
taking off their tail rotors, you're saying, or like
Yeah.
routinely?
well,
I don't know if
it's
that's
better
routine.
than crashing.
Sure, but what would make you think to look at this piece?
Because they had found it on this other helicopter.
Oh, I got you.
They discovered it on the other helicopter. They knew this group at Sikorsky told, all the other group chairmen of, the Blackhawks and the other people doing the MH-53s and, Sikorsky supplies 4 or 5 different basic helicopters. And this one group, and I think it might have been it's a scout helicopter, I can't remember the name of it, but it's a small helicopter that's just kind of a 2-man helicopter that goes out on scouting missions. And that one is where they found the problem, as I remember. But it was also the MH-53s or CH-53 and the Blackhawks. It was in all the rest of them, because they kind of used the same basic design. I also found a flaw in their analysis on their mechanics of their design, but that's not when I was looking at their data. But
Well, that was my other question. How do you know if you should be designing for your K1 or K1 SCC? Like, how do you decide ahead of time whether or not this is susceptible to stress corrosion cracking?
well, whoever chose the material was not thinking about stress corrosion because they wouldn't have chosen T6. Okay?
Right. What would clue you in to think, hey, I need to make sure I'm designing for stress corrosion cracking?
Because you're using aluminum alloy that's optimally aged. I mean, you need, a metallurgist has to tell the designer, who's a mechanical engineer, okay, that, you have to worry about it. You need a materials person signing off on the designer's design. I did find a mechanical problem in the designer's design. I don't have time to go through, but it's just, in big organizations, you have problems. We've heard some of your stories about people didn't tell so-and-so this. And people died sometimes because of this. But, again, the Navy's the corrosion leader. You guys will see it first. It was no surprise to me that the cracked ones on the shelf were Navy. Okay? You guys have a lot of salt air around. So, You always have to worry about it. Okay, so I think I'm actually traveling a fair amount for the next 3 or 4 weeks, although I might have some time to do a recitation, Tom. When you guys are ready and have done enough welding stuff, then we can do another class, and it'll just be a recitation where you guys can come in and ask questions. And if you tell me ahead of time some of the things you have questions about, I have a number of touchy-feelies, you know, that we can pass around. That's a piece of tantalum tubing. This is a piece of, if I had time, I was gonna show you, when you do the welding, one of the things is cold welding, one of the first lectures. And this is actually a piece of, they're gonna make tantalum wire, and they cold weld it together. And this is how they do it. They just squeeze it squeeze it again, and then you shear off this stuff. But we can later pass that around after you've done cold welding lectures, and you'll see, gee, it's just like they show in the welding handbook, only this is a real piece. And I asked them if I could have one. It's a little firm over here in Waltham, actually a big firm, HC Stark, in Waltham, not Waltham, but Newton. And about a third of all the world's tantalum goes through that plant. And it turns out there's an MIT story behind that, in that the mechanical engineering department at MIT in the 1940s developed a very high-speed vacuum pump based on steam injectors. Okay, it's what do you call these things? Anyway, you flow the steam through a little nozzle, and it creates, by Bernoulli's principle, it creates a suction.
Air injectors.
Well, you call them air injectors.
Jet nozzle.
Yeah, it's a jet nozzle air injector. There's another more sciencey name that I can't remember, but it doesn't really matter. It's an air injector, okay? And they invented this thing, and all of a sudden they could now do vacuum metallurgy. It turns out a lot of they weren't doing plutonium here, but they were doing uranium during the Manhattan Project, in part because we had vacuum systems that could melt these reactive metals. Titanium 6 aluminum 4 vanadium was developed over here at Watertown Arsenal in the 1940s. My thesis advisor did his thesis on tungsten, the purest tungsten in the world. I did mine partly on niobium alloys and stuff. All of this refractory metal alloys was done at MIT, started because of this developing the air injector for the vacuum metallurgy so they could melt these reactive metals under a vacuum. Before World War II, nobody knew how to use a vacuum system to melt a metal. The metals gave off so much gas that you didn't have a vacuum pumps that were big enough and stuff. The air injectors, they had enough sucking capacity. And so whole industries around here. There was once a place called Nuclear Metals, and they made all the depleted uranium projectiles. Okay, it's a spin-off of MIT. There's all kinds of spin-offs, and a lot of them go right back to that air injector vacuum system over in mechanical engineering that allowed them to do vacuum metallurgy, allowed them to get into reactive metals, built up the whole titanium business in a sense, made it possible because of vacuum metallurgy. That started out in mechanical engineering, which is your department. Okay, thanks. See you again.